Yesterday we already heard a lot of instances when the problem of deciding whether one orbit is lying in the closure of another arises. And I would like to discuss this problem in complete generality. And my point will be that of Hilbert, who trying to answer criticism by Gordon and Poincaré and others about theological nature of his proof of first fundamental theorem of invariant theory, published in 1890, big paper, trying to do the same, but using what we say now constructive approach to avoid just statements about existence. And he didn't bother about complicatedness of algorithm he was trying to find, about complexity. And my point will be the same. I will try to describe an algorithm answering this question in a constructive way, but I will not speak about complexity, and this is an interesting problem. It's a challenging problem, showing that there's a room for improving these algorithms to try to find another ones. So the setting will be the following. I will fix the ground field K, which will be algebraically closed, and I will not bother about characteristic. It may be arbitrary. At one place, I will require that it is 0, but I suspect that this is superfluous, and actually all the rest has nothing to do with restriction on characteristic. And assume that I have a finite dimensional vector space V over this field. Let n will be this dimension. And assume that I have a fine algebraic group, which I will assume connected, acting linearly and algebraically on V. So the problem which I would like to address is the following. Assume that I have 2 points in V, 2 vectors. How can we find out whether orbit of A lies in the closure of orbit of B, and find out in a constructive way? This will be the problem. Actually, you may say that, well, there are examples of the same question when such a group acts not linearly on a vector space, but on some, say, affine variety. Yesterday we had seen a lot of examples, so quasi-affine variety, or even more generally a quasi-projective variety. But I will explain that, in a sense, all these problems are reduced to this one. And briefly, the reason, say, for affine varieties is that any affine variety endowed with algebraic action of algebraic group can be equivalently embedded in a linear action on some vector space. The same is true for quasi-affine varieties, and of course, quasi-projective varieties cannot be embedded in such way. But there is a trick which nevertheless reduces everything to this case. I will explain this a little bit later. Before I will move to the algorithm, let me consider several examples. There were a lot of examples yesterday, but nevertheless, maybe it's worthwhile to consider a little bit more. For instance, this will be my first example. And this will be the following one. Assume that I'll use notation L is a finite dimensional vector space or over the same field. And I'm interested in the structures of algebras, this L being underlying vector space of such algebra. By algebra, I mean not necessarily associative algebras. Namely, there is a multiplication, and should be multiplication in L, which is just distributive, no other restrictions. And such structure of algebra is defined by an element of this tensor product, which will be my V in here, where star means dual space. And the definition is just the following. If you have an element in here, which is the sum of Li tensor L dash J tensor K, I, J, K, where this is in here, this is in there, and this is in here, then multiplication of two vectors is given just by definition by this formula. So this is an element of L. And this is structure of algebra. And all algebras are obtained in this way. The group G will be the full linear group of this vector space L, and it acts on this V in a natural way. And it's easy to see. Let me denote what will be my notation. Say L of V is algebra. This is, let me call this A. L. Algebra defined by point A. And it's easy to see that two algebras are isomorphic if and only if these 2 points A and B lie in the same orbit. So orbits they classify algebras up to isomorphism. And we can consider this question in this setting. And if we have this inclusion, then we say that, not we, it's in this theory of algebras, people say that algebra A is degeneration of algebra LB. And there is a big theory about degenerations, and people study when this degeneration given to algebras, when one is degeneration of the other, and it's considered to be a complicated question to decide in general. If we have two algebras, how can we decide whether one is degeneration of the other? But this is, in my language, is just the question of constructive deciding of this question star. Another example also comes from algebra, and this is as follows. Assume that L is the same, and its dimension, say, is D. And assume that I have a finitely generated associative K algebra. And I'm interested in structures of A modulus on L. So I'm interested in
on L?
on L. On L. This is can be considered as follows. If I fix here a basis, then linear operators on L are just matrices. And to define the structure of algebra on here is the same as to say how the generators, there are only finitely many generators of A by definition of finitely generated, is how they act on L. We should know this, then we know everything. And this means that if A is, say, A is generated by, say, M elements, then structure of A modulo on L is defined by M tuple of matrices of size D by D, which is just operators, by means the generators act on L. Therefore, if I consider space of matrices, this is square matrices of size D by D, n times then the structure of algebra on L is just a point in here. But this is not arbitrary point, because the generators in A are subject to some relations, and therefore the images should be subject to the same relations. And therefore we should consider only the M tuples which are cut off by relations to which generators of A are subject. And this cutoff here some subvariety. So closed subvariety whose points are just the images of generators under the structure of A modulus on L. And again, we can do the same, and if I use a notation, say point A in here, if I use notation mx, this is A module on L corresponding to point X, then the natural action of GLD on this space by conjugation split the X as a bunch of orbits, and orbits they correspond to A modular structure on L up to isomorphism. This is isomorphism of modulus if and only if G orbits are equal. And the same in this series is big theory, and for some specific algebras there are some answers. This is used the same terminology if this
small a should be an X, so typo. Small a.
Small, yeah.
Up there, no. Up.
A B, A B, A B. Okay. And if you have an inclusion, then we say that MA is degeneration of MB. And people study this, and in some cases there is answer when we have this inclusion. For instance, who is that? It's Bongard. Studied the case when A is a so-called path algebra of a quiver, which is extended diagram of type simply lace diagram of type A, D, or E. And path algebra is just the vector space is K algebra whose bases are just passes in this graph. And multiplication is given just by concatenation of passes if it is possible, or zero if it is not possible. So this is finitely generated algebra, and in this case, very specific case, there is a nice answer when this happens. But in general, this is again considered to be quite complicated question.
So is it any easier when A is free, so it just X is the whole?
That's right. That's right. If it's free, it's. But again, in some nice cases, it's possible to give the answer. But my point would be to input no restrictions on just to consider this problem in complete generality. Let me also mention the following application And also continue considering examples. Implication is the following. Application of considering this question. And the application is based on the fact that in algebraic geometry, orbits and their closures, they have nice property which doesn't hold for topological groups. Such phenomena like torus winding is impossible in algebraic geometry. And I mean, namely, I mean the property that orbit is open in its closure. And because of this reason, if we have both inclusions, then there's nothing but the statement that orbits are equal. But if we know how to solve this problem, we could solve it twice. In this case and in this case, if in both cases we obtain answer yes, this would mean the orbits are equal. This would mean, for instance, in this situation or in this situation, that we get a mean to decide whether two algebras, whether two moduli are isomorphic or not. And there are another examples of solving the problems of classification or equivalency using this approach coming from algebraic geometry. Let me give you a couple of examples. Namely, consider hypersurfaces in the projective space. So it will be example 3. And dimensional projective space, and then consider hypersurfaces. Given by equation where this is a homogeneous form in coordinates on Pn, irreducible. I also would like to impose a constraint that I consider only smooth hypersurfaces. And it follows from the classical theorem by Severi, Andreotti, and Lefschetz that if d, which is degree of x, is bigger or equal than 4, and n is also bigger or equal than 4, then such hypersurfaces h1 and h2, x1 and x2 are isomorphic as algebraic varieties if and only if the corresponding forms, so this is locus of f0, f1, and this is of f2, and f2 are in the same GLN plus 1 orbit, acting naturally on projective space. So we reduce the geometric question of isomorphism of algebraic varieties to the question of the type which are considering. We have linear representation of GLN plus 1 on the spaces of forms of degree d in n plus 1 variables and ask whether they are in the same orbit or not.
What happens in lower degree?
Well, there are some exceptions. But this is just precisely this case. If we can answer the question of if we can solve the problem star and apply in this situation, then we can answer it in principle this question whether.
Can you just tell me the example in degree 3?
Oh, I don't remember by heart, but there are some.
The plane elliptic curve.
All right.
Oh, so this is isomorphic as abstract variety.
It's abstract variety. It's abstract variety.
Isomorphic as abstract variety.
No. Maybe I said this. No. It's abstract variety.
Yeah.
It's abstract variety. So this is would be the solution. And the last example is by smooth projective curves. Smooth projective curves. of genus G bigger or equal than 2. Let's consider such reducible curves. By triple of canonical class, every such curve is embedded in projective space, so 3K, 3 times canonical class embeds such a curve in projective space of dimension 5G minus 6, where G is a genus. So curve sits here. And it is known that curves are isomorphic, again as abstract algebraic varieties. If and only if images of these embeddings are in the same orbit, are transformed one to another by means of projector transformation. Transformed by projective transformation, one to another. But one can associate with, define actually such an image by its Chow form, which is some hypersurface, like here. And again, this condition is the same as transformation of one Chow form to another Chow form. And therefore, we are in this situation and can apply this. So in principle, this gives you the way to decide whether two curves of this type are isomorphic as abstract varieties or not. Okay, this is my examples. Now, I would like to discuss these. And for this, this will be some algorithm. But in every algorithm, I should know what is known, what is input, and that will be output. Therefore, let me first describe, say something about input. First of all, I will fix a basis in this vector space, V. And I will illustrate what I am speaking about by means of considering the classical example of binary forms, which was the subject of study of classical researchers, and illustrate all the things which I am speaking using this example. So we'll fix a basis here. The case when dimension is 1 is trivial, so let me assume, so it's easy. So from now on, and I will assume that n is bigger or equal than 2. If I fix the basis, then the action of G is described in matrix language, namely every element of G is mapped to linear operator on V. And linear operator, when we fix the basis, is a matrix. So you have action given by homomorphism of G, algebraic homomorphism of G into GLV. And GLV, because of this basis, will be identified with space of matrices, G and K. And therefore, every element is mapped to a matrix, and the matrix has matrix entries, which depend on G. These functions, G is mapped to rho ij of G, is a regular function, polynomial function on my algebraic group. So I will use notation for regular functions. This will be my standard notation, not O of G, but K of G. And I will assume that these functions are known to me. I'll consider example and you will see what's going on. Now, further, I need a notation. Let Rs, voltphase A raised to the power Rs, will be an open subset in affine space of dimension R plus S. Such that first R entries are non-zero. So what I'm doing, I'm just throwing away from this coordinate affine space several coordinate hypersurfaces. And the open set which I obtain is denoted in this way. I'll denote by xi standard coordinate functions on this space, and given by condition that its value on this tuple is epsilon r. Then algebra of polynomial regular functions on this affine variety is generated by x1 r plus s, but first r axis they are invertible, so they are regular therefore. So I have to add them. So this is this algebra. And all possible monomials of the type x1 raised to a1 r plus s, where I1, IR are any integers and the rest are natural numbers. All possible monomials is the basis of this infinite dimensional vector space over my field K. It's the basis. Over I will now use the following remark. Let me call it lemma. So I call you that I have a fine algebraic group connected and no restrictions on G are imposed. And the lemma is the following. For some R and S, there is a dominant regular map of this variety into variety G. Moreover, I do not need, there is some freedom. You can, I need to fix some map, let me call it iota, some map of this type, but there are plenty of them, and among them there is even an open embedding. And I will not use it, but just as a remark. I will fix such I and work with it. If I is fixed and these functions are given, so then I have, this will be functions rho ij, and this is my iota, which gives me the functions iota star rho ij, which will be regular functions on this affine variety, which are therefore some linear combinations with coefficients in k of these monomials. Yeah.
What is iota and RMS would be just in the case that G is GLN?
You are a bit ahead of me. I will give you an example in 10 seconds. So this is some functions lying in this algebra. So I will assume that they are not only this row ij are known, but these functions are known, etc. Let me consider example of binary forms. Okay, assume that they are known to me. Example. My G will be SL2. And my V will be space of binary forms in two variables, as example. Let me call it VH, so this is binary forms in variables. I will denote them by Z, Z1 and Z2 of degree H. This is H plus one dimensional vector space. And group acts, so if G is matrix alpha, beta, gamma, delta, then the action on the first variable is alpha Z1 plus gamma Z2, and on the second is beta Z1 plus delta Z2. So this is how it acts on this vector space. And as an example of such iota, I will consider the following map. So it maps to this three-dimensional epsilon 1, epsilon 2, epsilon 3. It maps to a matrix. And matrix which I would like to consider will be the following. This will be 1, epsilon 2. This will be diagonal matrix. So this will be so if you multiply, you will get the following: epsilon 1 minus 1, epsilon 2, epsilon 3, epsilon 1, epsilon 1 minus 1, epsilon 3, epsilon 1 minus 1, epsilon 1 minus 1, epsilon 2. And when these epsilons vary, then you may see that the whole totality of this matrix is dense in the SL2. So the map is indeed dominant, as I need. So it's a dominant map.
This looks like it'll give the general proof too, right?
Yeah, but absolutely. So this is simplest example of what is called Brouillard cell, big Brouillard cell in SL2. So in any group, in any reductive group, there is such a phenomenon. These functions rho PQ, rho IJ, are defined in the following way. Let me just give you the answer and skip the rest. So these monomials Z1, Z2, this is degree H minus J and J. This is monomials when G runs from 0 to N, to H. They constitute a basis in the space of VH. And such a monomial under the transformation G is obtained if you plug in, instead of Z1 and Z2, these forms, and erase it and expand. So the result will be rho I plus 1 because I count the entries of the matrix not from the 0 but from 1. J plus 1 G Z1 H minus 1 Z2 I. So this is my functions. But if I would like to have iota star of these functions, then the recipe will be the following. You should you should do the following. You would have to, using this matrix, take x1 plus x1 minus 1, x2, x3, z1 plus x1 minus 1, x3, z2. Raise this to h minus j, x1 minus 1, x2, z1 plus x1 minus 1, z2, and raise it to g. And this will be sum of monomials in z1 and z2 with some coefficients. And these coefficients are just precisely these functions, which I'm interested in. For instance, if h is 2, and you expand it, then I star of rho 2, 2 will be 1 minus 2, x1 minus 2, x2, x3. So this is just very explicit. And I assume that these functions are known to me. So this will be 1/2 of the input of the algorithm, these functions. Another part is just one number, which has geometric meaning. And I will denote it by D. And it's in this place where I will assume that characteristic is 0, but I suspect that this can be redundant. It can be dropped actually. But let's assume, because I will use some result by Kazarnovsky in which he uses this assumption. Actually, he uses the assumption that the field is C, but I suspect that this is not really important. So anyway, the second part of the input. So this is first part, these functions. And second part is just one number. And this number is D, which is degree of this thing, which sits in GLN, K, which sits in the space of matrices of size n by n, which is nothing but n squared coordinate vector space. So this rho G is algebraic subgroup in here, and it's known as it's closed in here. Therefore, we have in this vector space some algebraic variety, this one. And every algebraic variety, in particular this one, has a degree. Degree is the following thing. So in a vector space, you have algebraic variety. And then you take a hyperplane of the complementary dimension in this vector space. It intersects somehow this variety. And almost for all such hyperplanes, for generic hyperplanes, the number of points of intersection is the same. And this number is called degree. So once again, you have your variety intersected with a fine subspace of a complementary dimension, and count the number of points of intersection. And it appears, it's a theorem, that for almost all such affine subspaces, this number is the same. This is degree. And I need to know this degree.
So is there a way to compute this in general for groups?
This is what I want to explain to you. So it's possible to answer what is it. It appears, so I need this number in my input. And it appears that it's possible to calculate it. I am afraid that I don't really have time to do this. I have to finish in 8 minutes, right?
10 minutes.
10 minutes. Then let me put it like this. Since this is just sort of preparation, so I explain you what is the input, but then the algorithm. Let me postpone. If I will not have time, then just to those who are interested, I will explain that this D can be calculated explicitly. In particular, I plan to consider example of binary forms, this one. And using this result, one can obtain the following answer. This is just a matter of calculating some integral, elementary integral, which students do in calculus. And the answer will be the following: degree of rho of g in this case will be twice h cube or h cube, depending whether h is odd or even. It's calculatable, can be calculated. Next remark, again, I have no time to explain this. Not difficult, but should be explained in more details. Since I have no time for this, let me just formulate a remark. In problem star, this one, I can always assume that A and B are non-zero points. Zero is not there. And orbits are conical.
A also is assumed to be non-zero.
Say it again.
A also is assumed to be. It would be interesting to understand the case.
Here?
A is equal to 0. Yes.
They can, nevertheless, both are not equal to 0. Replacing V by another vector space, you can reduce this to the case when both are non-zero and the orbits are conical.
A is equal to 0 is interesting.
Right, but A is equal to 0 in V, but in another space it will be not 0 if you this is what I mean. So replacing V by another vector space and G by another group, you can reduce this to the case which I specified here. Both are non-zero and conical. So let's assume this. Again, I have no time to explain. And now finally the algorithm. So I have degree, have these functions, and assume that this holds. And now what about the algorithm? The algorithm is the following. One extra remark is the following: changing basis, we may assume, may and shall, that B, which is beta 1, E1, beta n, En, has the property that all coordinates are non-zero. And I also assume coordinates for A, alpha 1, E1. So these coordinates alpha and beta are known to me, and I assume that all betas are non-zero. So step 1, consider n polynomials, f1, fn of degree 2d minus 2. D is known to me, so I can do this. In variables, new variables, y1, yn. So this will be like that. Some coefficients, sorry. This p is 1n. And these are some natural numbers such that their sum is at most 2d minus 2. And these coefficients will be also variables. They will be algebraically independent over k. So for me, at the moment, these y's are variables, but these coefficients, so these are generic polynomials. They also have the property that all this c, they are algebraically independent over k. From these polynomials, I need this because from these polynomials I will cook another one. Namely, I call it h.
Excuse me, what's the degree on this? I can't read it. Sum of the cubes is less than
2D minus 2.
2D,
Thank you. 2D minus 2 is the degree.
2D minus 2. So consider just one polynomial made of these f's, namely the following: y1 minus first coordinate of my point A, alpha 1, times f1, plus etc. yn minus alpha n fn. Consider this polynomial minus 1. It will be h. Step 2. Plug in this polynomial in place of y the following thing: beta, which are coordinates of my b. Then here I use these functions which are known to me. So I plug in instead of these y's, this guy, and expand. The result will be sum of, so these functions, they are functions in xi's, which are the functions on this standard, so to speak, affine space with removed coordinate hyperplanes. So this will be sum of monomials in these xi's. In some coefficients which I'll denote by L. And the remarkable thing that you immediately see this, that these L's, they are linear forms in this coefficient C. We never raised C using this approach to some power. We just plugged in. So this is a linear form in this coefficient C. And now I'm ready to give the answer theorem. The following properties are equivalent. First property: orbit of A lies in the closure of the orbit of B. This is what we are interested in. And second property is the following: consider system of linear equations which are just these L's. Equal to 0. System of linear equations. And the requirement is that this system is incompatible. There's no solutions. Using Kronecker-Capelli theorem, this means that the ranks of corresponding matrices are different, which is possible to verify. And this is equivalent to this geometric property. One orbit is sitting in the closure of the other. That's it. So I should stop here because of the time reason. I'm sorry that I had to skip these details about D. This is very nice. The answer is very nice. But this.
So could you at least give the idea of how you compute the degree of rho of G?
I think the magic is that there's a degree about it.
Just the idea.
First of all, it's a theorem of Kazarnovsky, as I told you. It's not me.
So could you state maybe the theorem?
Yes, but for this I need some notation. But since we have discussion and therefore some 10, 15 minutes, therefore I can spend it for more formulation. Or not? Yeah. Okay. Okay.
Maybe you can just explain how you compute this degree.
Maybe, but they want to see the formulation of the theorem. Maybe I'll do this, and then you. If
Maybe
you
be more precise in the private discussion.
okay. But should I formulate the theorem or not?
Formulate it.
Okay.
Is there not like a simple statement if you compute the Hilbert polynomial of the variety and look at the first coefficient?
You do that use by integrating over the polytope.
This is actually using the modern language. Computing this degree is related to the theory of spherical varieties, intersection theory on this spherical varieties.
That's satisfactory.
This is what is hidden there. This intersection theory on spherical varieties. That's it.
There's another question.
Yeah, so what seems striking here is that you have this degree bound, that it's 2D minus 2, you just need to look at n generic polynomials.
Okay.
That seems to be what's...
Okay. Again, just short remark, just to give you some. I use in the proof efficient form of Hilbert-Null-Stellensatz,
Okay.
and it comes from there.
It's that simple.
And this is result by Jeloniek, who obtained such a form, and then I applied.
Any questions or comments?
So I don't understand this incompatibility condition. You just mean that the rank is full of the linear system.
Incompatibility.
Non-trivial solution.
Non-trivial. So what mean non-trivial? Just no solution at all. It's not. It's not homogeneous.
Oh, it's not homogeneous.
No, I didn't say this. It's just linear system.
Okay, good. So suppose there is a solution.
Yes.
Which is, I mean, it's if and only if. So suppose there is a solution,
Yeah.
then there is no containment. But suppose the solution is with integer values, something like this. And you assume that the solution is the coefficients of your polynomials. You assume that they were algebraically independent.
No. The solution is not coefficients of my polynomials. Coefficients of my polynomials are variables of this system.
Yeah. So solving it means giving values to this coefficient, right?
Given values to this coefficient, precisely.
Suppose there is a solution.
Yes.
And the solution is, let's say, integer.
Okay.
So all one vector.
Yeah.
They are not algebraically independent, which was an assumption in the construction of the polynomial.
Oh, that assumption was just to make variables. Just make some variables.
This is a way to make variables for system of linear equations. This is where I'm taking from these variables, from these coefficients, and that's it. Well, if you have system of linear equations, its variables are independent, right? But it may have solutions which is not independent. That's just precisely this.
Luke has a question.
I wonder, can you just advertise the results of this theorem of what orbits have you been able to separate or not using the method? Like, do you have a list of orbits that you're successfully...
Well, this concerns, well, if you remember, I started my lecture with the remark that I didn't bother about complexity. I didn't. So if you apply this, for instance, to binary forms, and try to figure out what it gives in here, you'll obtain enormous amount of variables of this system, an enormous amount of equations. If I remember correctly, if you take binary forms of degree 4, then this method gives you a system in which the number of variables is something like 56 millions. It's huge. It's very, very big. So applying this in, but this is like just precisely the same situation as with Hilbert's proof of the first fundamental theorem. He proved that this is possible to do, but if you try to apply this in concrete situations to binary forms of small degree, you are killed more or less quickly. It's not directly applicable for practical purposes.
So then you criticize your own theorem. You must have something that you like.
I didn't criticize. I just. There should be some person like I don't know who expert in complexity theory. But this is, as I told, the area where you can try to move further to improve. This side of the problem, but I didn't attempt this. So far, at least to my knowledge, so far it was just some necessary conditions, when one orbit is not in the closure of the other. But now this is just the if and only if.
Okay, no more questions?
Maybe you said that you use this effective Nullstellensatz, this yellow leg. But these bounds of the degree are always exponential in the number of variables in this effective Nullstellensatz.
Yes, why is
I don't see this in your results. So is it somewhere hidden or?
But how can you see how? What is the way to see could be the way to see this?
The number of coefficients in the extra equations that you gave were higher degrees.
As I told you, the number of coefficients is huge. It's.
I see these are these
Let me take a look at.
the coefficients of these generic polynomials. There are just many.
That's right. That's right.
But the degree is not that big.
Degree not that big, but the number.
Coefficients.
The number. That's right.
But still, it could be worse. I mean, it could be that the coefficients are many and the degree is very high, but it doesn't seem to be the case.
You see, it's not asymptotic, but just to give the flavor of magnitude of this. So in the case of binary forms, the number of variables can be with some coefficients. It's something like h to the h twice h, something like this.
What is this?
H is binary forms of degree h, and the number of variables is something like this. It's a huge number.
Okay, now
H to the twice h, and this is e to the h.
Okay, so one last question.
Yeah, might be with respect to Peter's. So for this orbit closure problems or closure of anything being contained in another, I mean, there is obvious, well, not obvious, but algorithms from quantified elimination that allows you to decide that, right? And then those will be singly exponential in the dimension, because these are constructible sets, and you want to say that the closure of one is contained in the other. So what I want to say is that there is always some singly exponential algorithm.
This is an interesting question which I would like to figure out what one could expect here. Is it because something huge should be here, or is it because of the method is bad? This I don't know. For instance, in the case of invariant theory, when Hilbert obtained his bounds, upper bounds of the degrees of polynomials, well, it gave again huge number of calculations, and was not because of this reason was not applicable from a practical point of view. But only the recent developments showed that this is not because method is bad, but because algebras are complicated. And it is strict mathematical statement. One can explain what this means. Because there's a lot of usages there, and it's just complicated algebras. And I don't know what is hidden here. Is it a similar story? Is it because the problem is really, or our methods are bad? I don't know.
Okay, so maybe we thank you again.
So when you H is a called